Hello, everyone, and welcome to today's webinar entitled 5G Promises the Massive IoT, but Do We Have to Wait for 5G? Presented by Qualcomm. I'm Tara Sills, contributor to Fierce Wireless, and I'll be your moderator today. Our speaker today is Hao Xu, who is Principal Engineer for Corporate R&D at Qualcomm, and you can read his full bio on the right-hand side of your window there. Just a few technical notes before we begin. If you have trouble reading a slide, you can just hold and drag the right corner of the slide window to enlarge it to make it easier to read. And if you'd like to download the slide deck, you can certainly do that. Please just click the resources button at the bottom of your screen and follow the prompts. Also, the webinar is being recorded and will be available on demand within about 24 hours after the event, so you can share it with your friends and colleagues. And finally, we're going to follow the presentation with a Q&A session. So please feel free to submit questions anytime during or after the presentation. Just use the Q&A widget at the bottom of your screen. And with that, I'll turn it over to Hal to kick us off. Welcome, Hal.
Yeah, thank you. Thank you very much for the introduction, and welcome everyone to our presentation. So today we'll talk about how lte-IoT and its evolution fits into the vision of connecting the massive Internet of Things. So we'll spend the first 45 minutes on the presentation, then roughly 10 to 15 minutes on the questions. The overall presentation will have three main sections. We first provide an overview of IoT and address some of the fundamental questions. For example, why lte-IoT is important, what are the key requirements and technical challenges, what are the key differences and the common ground between eMTC and nb-iot, how does it fit into the 5G platform, what are the new techniques we're considering for 5G, and what are the new horizons such as unlicensed deployment and industrial IoT. So that is the main overview section where we provide the background and the main directions. The second section will take a closer look at the technical details. Specifically, we'll review the evolution path starting from 3GPP release 13. Then we'll focus on the technology inventions coming from release 14 and 15, as well as a sneak peek into advanced features for release 16 and beyond. But last but not least, we'll talk about the current status of the ecosystem. We'll provide a quick overview of the worldwide lte-IoT adoption with a snapshot of today's operators' deployment plans for eMTC and nb-iot. We'll also review the products available today and discuss the trade-off among single mode, multi-mode, and global multi-mode modems. So with that, we'll start our presentation. So what is IoT and why is it so important? Looking at the cellular industry evolution, we started a few decades ago to connect people to one another, mainly via voice communications. That was the main focus of the first and the second generation of wireless communications. Then we extended the connectivity to the mobile internet. This is the focus of 3G and 4G data communications. And now we are at the beginning of a new era, the era of the Internet of Things, where we're connecting everything in the world. So based on some market research, it is predicted that the world will have 25 to 50 billion connected devices by the year of 2020. So we are expecting a rapid growth of IoT applications in the coming decade. In fact, currently Qualcomm is shipping more than 1 million IoT devices per day, and we have already shipped over 1.5 billion IoT devices globally. So IoT encompasses a wide variety of applications and devices with different requirements. So some can be better addressed with shorter range indoor connectivity, for example, Wi-Fi and Bluetooth, while others are optimized for wide area applications like cellular. In this presentation, we'll mainly focus on the cellular technology-based IoT. There isn't one-size-fits-all connectivity technology, but what is important is that we require heterogeneous connectivity solutions that are backed up by the global standard. So this way, we can ensure a seamless interoperability across vendors, regions, and devices. And we'll get into the details of this aspect in the later presentation. And we're at the heart of the IoT ecosystem, where we provide all the wireless technology for the IoT ecosystem. So what are the main advantages of cellular IoT? For wide area applications, as I mentioned earlier, there are different types of IoT devices, applications. Some of them only need near-field communication, and Bluetooth or Wi-Fi would suffice. But for wide area applications, cellular technologies can enable new services that can cut across markets and industries, such as new use cases in smart cities, mobile health, asset tracking, just to name a few examples. So the first benefit is that wireless cellular IoT is always available. It's ubiquitous coverage for both indoor and outdoor deployments. In fact, IoT coverage enhancements features provide 15 to 20 dB enhancement even beyond today's LTE. So if today's LTE's maximum coupling loss is 140 dB, with IoT, eMTC, or nb-iot, the coverage enhancement level can be 15 or 20 dB more, which is in the range of 165 dB maximum coupling loss. So that is between the NOB and the end device. As we already mentioned, LTE is a mature ecosystem backed up by global standards. So this is particularly important when we want to connect different types of devices across different regions in the world. As we all know, cellular technologies such as LTE are scalable in nature, and a wide range of services can be supported with a single unified network, which minimizes maintenance and management. Security is another important aspect. We all know that cellular networks already deliver end-to-end security required by the most demanding users, such as governments and financial institutions. So the total number of cellular connections for IoT M2M is expected to exceed 5 billion by 2025. That is growing rapidly from today's around 450K in 2016. And this translates into about 30% of compound annual growth rate. So what are the main technical challenges for IoT? Historically, cellular design always focused on higher spectral efficiency. We always push for very high MIMO, very high carrier aggregation, and very high throughput. And that is to meet the demand for the high throughput applications like video streaming and so on. IoT, on the other hand, poses some unique requirements, which is quite different from current traditional cellular design requirements. We can briefly view this as four main pillars: coverage, coexistence, complexity, and power. So to focus on some more concrete technical details, coverage target is 164 dB maximum coupling loss. And this is targeting deployments in basement. For the meters, for example, water meters or electrical meters in Europe, some of them are deployed in the basement. Or this is targeting rural area where we can deploy very large cell size in order to reduce the deployment cost. So the coverage enhancement of 20 dB, 15 to 20 dB above LTE is viewed important for this kind of IoT deployment and applications. The second pillar is the massive scale. 5G requires, for example, in the 5G requirements, 1 million devices per square kilometer is specified. This is quite challenging from capacity and latency point of view, and we need to optimize both the network and device to achieve that goal. The third requirement is complexity reduction. In the 3GPP work item description, for example, the initial goal was to have the price target comparable or complexity level comparable to 2G. On the power consumption side, our target for IoT is 10 plus years of battery life. Obviously, this is quite challenging. Comparing today's cellular phone battery life, which typically lasts for 1 day or no more than a few days, this is quite some challenge. And we'll discuss more details how to achieve this. 3GPP has actually started looking at LTE-based IoT from release 12, where the category 0 was introduced, even though substantial work started only from release 13, where both eMTC and nb-iot are specified. So LTE provides a scalable IoT platform into two directions. You can view Cat 0 as the middle or the boundary point between high-end and low-end devices. On one hand, high-category UEs can scale up to support gigabit wireless through MIMO, carrier aggregation, and other advanced techniques. On the other hand, we specified category M1 and category NB1 in a negative category region. For example, category M1 started by using -1. That's where M comes from. So in a negative category region, where we try to reduce the complexity and cost. I often get a question on why they're both eMTC and nb-iot, and what is the difference between the two. As we discussed earlier, the variety of IoT use cases, ranging from security camera to meter reading. In fact, eMTC and nb-iot are complementary, and they are designed for different types of IoT use cases. Category M1 delivers peak data rate up to 1 megabit per second, utilizing just 1.4 megahertz of bandwidth. This 1.4, by the way, is specified in release 13. In later releases, there are also other categories defined where we can target even higher bandwidth. On the other hand, for Cat NB1, it scales down even further to deliver just tens of kilobits per second for very low throughput and delay-tolerant applications. So you can see there's a clear trade-off between the peak data rate supported by these devices and the device complexity and cost. So that was the consideration when we designed two different techniques and standardized both eMTC and nb-iot. So how does lte-IoT fit into 5G platform, and how does it impact 2G and GPRS? lte-IoT is starting to connect a massive number of IoT devices already today. We see 5G NR, the new radio as defined by the 3GPP, starting in release 15, but the main focus will be eMBB and URLC. eMBB is the enhanced mobile broadband, and URLC is ultra-reliable, low-latency communications. So the initial massive IoT solution will be with lte-IoT, which continues to evolve beyond release 13. The 5G NR acceleration and lte-IoT evolution is actually complementary for the IoT, with many high-performance IoT applications can be addressed by 5G NR, but the low-power, wide area use cases will continue to be supported by lte-IoT. So on the coverage front, we see that LTE networks deliver today ubiquitous coverage, but 5G NR networks will only become available starting 2019. So it takes time to expand the coverage for the IoT. This makes LTE the platform of choice for wide area IoT, and it is also the anchor for the 5G experience. The lte-IoT evolution also serves as a good migration path for 2G GPRS networks, which is getting reformed so that we can utilize the valuable spectrum resources more efficiently. This is actually already happening today and around the globe. In this slide, we provide a summary of continued evolution for lte-IoT. As we mentioned earlier, the fundamental features of eMTC nb-iot, they're all introduced in release 13. But then many new features and enhancements are adopted in release 14 and 15. And this slide lists some of the features in release 14 and 15. For example, we introduced the positioning and introduced the multicast. Besides licensed eMTC and nb-iot, there's also an ongoing effort to deploy eMTC and nb-iot on unlicensed spectrum. This is being defined in the Multi-Fire Alliance. We can also see that 5G NR-based massive IoT design, which introduces more drastic changes, and it is expected to come in release 16 or later. So all this will fit into the 5G platform as different versions of the IoT offering. For release 16 and beyond, we can consider more advanced techniques. For example, some of the new techniques are considered to further optimize massive IoT. Two examples we're showing here. 5G will improve upon lte-IoT's capability to support even higher node density by introducing non-orthogonal multiple access techniques. One of the such techniques is called resource spread multiple access, or RSMA. The main idea is that we'll provide grant-free asynchronous non-orthogonal transmissions, which allow us to scale towards extremely large number of devices. By non-orthogonal, when we have an orthogonal allocation, then all the devices has to occupy either different time, frequency, or space, and they occupy some resources in an orthogonal manner. But if you have a large number of devices and in low SNR regime, you can actually schedule users on top of each other. And that is the idea of non-orthogonal multiplexing. The other key direction for the advanced technique is mesh network, where we look at different network architecture. So they extend network coverage for IoT devices to the most extreme locations, for example, deep underground, hyper remote, and so on. For the multi-hop mesh allows out-of-coverage devices to connect directly with devices that can relay data back to the access network. This essentially creates an edgeless network that extends coverage beyond the typical cellular access. Another new horizon we're trying to exploit is unlicensed spectrum. And we're introducing private LTE networks. Private LTE networks are composed of small cells operating locally in the premise using dedicated radio equipment. This makes the private network independent of traffic from other users, and you can control which data stays local and which data is sent to the cloud. Another important benefit is that you can tailor and optimize it for the specific local applications, such as guaranteed QoS and the latency requirement. In contrast, a public macro network is set up to provide generic coverage and usage. The good news is that there is already spectrum available today to run private LTE networks. For example, CBRS in the US at 3.5 gigahertz, and a multiplier in the global 5 gigahertz unlicensed spectrum. Of course, operators can also offer private LTE services using portion of their licensed spectrum. Deploying a private LTE network is similar to providing a Wi-Fi network. The core network can be hosted by a service provider, but if preferred, can also be run on a self-contained network locally. Deploying a small cell of self-organized network feature is now more complicated than deploying a Wi-Fi access points. An important detail is that even if you are using private LTE network for the local services, you can enable selected IoT devices to use the macro network for wide area mobility. So this concludes the first overview section. And on the second section, we'll take a deeper dive into the narrowband lte-IoT technologies. We'll first quickly go through Release 13 eMTC and nb-iot. Then we'll focus on the enhancement of Release 14, 15, and beyond. So here's a high-level overview of eMTC, nb-iot in different releases. One interesting trend is that nb-iot and eMTC, even though they are standardized as two separate work items throughout Release 13, 14, and 15, they actually share many common design techniques. As I mentioned earlier, many of the requirements are shared between these two technologies. For example, on the low-cost front, we can have single RX antenna, half duplex. These two techniques actually are common for both eMTC and nb-iot. On the power saving side, the power saving mode and the enhanced EDRX, they can apply to both nb-iot and eMTC. The coverage extension techniques, even though we have a different target for nb-iot and eMTC, where nb-iot is targeting even larger coverage enhancement. But the key technique is similar. Basically, on the physical layer design, both of them will use the so-called lte-a bundling. Basically, you repeat the transmission over time in order for the device or the node B to accumulate enough energy to combat either interference or thermal noise. So this shared foundation actually expands further in future releases. If you look at Release 13, some of the foundations are shared for the things I listed. In Release 14 and 15, the shared common techniques are even broadened. So in parallel, the Multify Alliance is also standardizing lte-IoT in the unlicensed spectrum, leveraging eMTC nb-iot in Release 14. And the future improvements in 3GPP will also propagate into future releases of unlicensed IoT. So here's a more detailed breakdown of how the four pillar requirements are achieved. Since we have discussed these techniques in previous presentations, I will not get into too much details here, but just highlight some of the important aspects. One of the key techniques to get low cost is we introduce narrowband operation. For eMTC, that is 1.4 MHz as a main mode, and for nb-iot is 200 kHz. We also added many options to reduce complexity, such as single RX, half duplex, and the core network can also simplified to optimize for the small data burst transmission. The long battery life is achieved by the power saving mode and the extended DRX cycles. So basically, this is extending the current paging cycle or DRX cycle by a significantly longer period. So the UE can sleep much longer if there's no urgent data transmissions. On the coverage side, we pushed the coverage to 15 to 20 dB beyond current LTE coverage. And this is mainly targeting the basement deployment and the rural area large scale. And the last aspect is the massive scale and the signaling network optimizations, for example, overload control to support large number of devices in the cell. So this one is a recap of the techniques for reducing the complexity. The main techniques I already mentioned, the peak data rate reduction, bandwidth reduction, and also for some technologies, we actually even sacrifice the mobility support to get even lower cost. And one important aspect is voice support. For example, in higher categories, voice is always supported. and voice supported for eMTC, but not supported for nb-iot. On the power saving mode, there are two design aspects. The power saving mode is providing the UE, the longer sleep cycle, but when UE goes to a so-called deep sleep mode, UE will not check paging or anything from network side. So in the deep sleep mode, the user will not be reachable. So this is ideal for applications, for example, a meter reading, where you transmit once per day to report the meter reading, and during the day you don't need to wake up. So this kind of technique will allow 10+ years of battery life for the device deployed in the field. But if you have an application that has some latency requirement, then extended DRX is a different way to achieve power saving. Basically, extended DRX is allow up to 40 minutes of idle mode DRX, or this is much higher than today's 2.56 seconds of paging cycle. So comparing 40 minutes and 2 seconds, you can see there's a large saving available for extended DRX. So deepening coverage, this technique is considered for both eMTC and nb-iot. The minor difference is that nb-iot will push for even higher 164 dB target rather than 155. And we need to know that even though the specification target was 155.7 dB for Cat M1, in fact, when we standardized this technology, we provided enough margin in the bundle size. So it is potentially possible for Cat M1 to extend beyond 155.7 dB as well. Next one is on the device density. We actually are increasing the device density to optimize for better network efficiency. So one aspect is we'll have a new access control mechanism, such as extended access barring, to prevent devices from generating access requests when network is congested. One important aspect is this IoT service will be provided together with other LTE or 5G services. And when we have a massive amount of IoT devices, we want these massive devices to coexist with other service we're providing. Whenever there's a more urgent service than IoT, we have a mechanism to control the access for the nb-iot or eMTC or any other IoT technology. So this is important to have the coexistence of different services. The second aspect is we'll have a simplified core network. As we mentioned earlier, we did a lot of things to try to simplify the device cost. But on the other hand, we also want to have a network that can be easily operated and deployed. So there's a significant amount of work done also in the core network side, and we specify the simplified core network or EPC Lite. The last aspect is the enhanced resource management, where the network can allow a large set of devices to share the same subscription, such that resources and devices managed can be consolidated. For example, a group of water meters in a smart city can be connectively provisioned, controlled, and built. So even though we have two different technologies, both of them will work with in-band LTE. For example, if we have a regular LTE data service, say 20 megahertz, we can have 1.4 megahertz within that 20 megahertz for eMTC, and 1 RB or 180 kilohertz within narrowband, within normal LTE carrier. nb-iot, in addition to the in-band mode, also specify the guardband mode of operation. Because it's so narrowband, it is potentially possible to put the nb-iot on the edge of the regular LTE data. And that's what we call the guardband deployment. And lastly, nb-iot can also be a standalone operation. Initially, nb-iot was designed to fit into the 2G GPRS bandwidth of 200 kilohertz. So from that perspective, it will be easy for nb-iot to replace some of the 2G and GPRS spectrum. This way, we can reform the spectrum currently used by 2G and GPRS, and we can use that spectrum a lot more efficiently. There's a rich roadmap of enhancement in 3GPP for release 14 and 15. Some of the major features are included here. For eMTC, it was considered, one of the use cases considered is for voice communications. And we provided the enhancement for VoLTE. For wearables, for example, you can have a smartwatch with the eMTC chipset where you can easily talk to the watch directly instead of always have to carry both the watch and the phone. On the other hand, for the nb-iot, as I mentioned earlier, in release 13, mobility was not fully supported for nb-iot in order to reduce the cost. But now we did further enhancement to support voice, to support mobility. So eMTC and nb-iot actually share some common technology enhancements. That's listed in the middle. So single cell multicast, this is important for the software upgrade. The key technique is to have one cell base station broadcast or multicast to multiple UEs simultaneously. And there are also other techniques, for example, lower latency. In the earlier releases, the HARC processing timeline is quite long because we want to reduce the processing horsepower and reduce the complexity. But in this release, we increased the HARC processes, and also we increased faster system acquisition time, and also we are considering early data transmission. This is basically transmit data in the early part of the RAG procedure so that UE can go to sleep much earlier and also can reduce the latency. The other important aspect is device positioning. So many techniques, many applications require positioning. For example, the asset tracking, where you need to know where the device is. So we have provided nb-iot and eMTC based device positioning. This is either can be deployed standalone without the GPS, or can be used together with GPS to further enhance the location. Next aspect is the energy reduction. This is considered for release 15 as a major enhancement. For example, one can use a so-called wake-up receiver or wake-up signal to indicate the UE for the wake-up or go to sleep. So this wake-up receiver can be much simplified than the traditional way of paging the UE. The other aspect is the higher data rate. For eMTC, for example, we are introducing a 5 megahertz support so that we can provide services and IoT applications with even higher throughput and data rate. Then the higher density support, where we have also considering enhanced access barring, as I mentioned before. This is in order to control the priority of access to the network. On nb-iot features, we have two important features considered in the 14 and 15 releases. One is cell size extension. Initially, nb-iot design, especially the RAS design, limits the current nb-iot cell size. And with the new enhancement, we can support up to 100 kilometer cell. And one of the other important features is for nb-iot TDD support. As we know, nb-iot in the first release only had FDD support, and eMTC had both TDD and FDD. And this TDD support is being considered for release 15 as an enhancement. So this slide talks about the new device categories. And we had M1 and MB1 defined in release 13. And now we're actually introducing category M2 and MB2. Basically, they are enhanced categories to support better data rate. Of course, the complexity will be slightly higher, but they can provide data rate which is significantly higher than current 1.4 and 200 kilohertz versions. And potentially, we can also have potential new categories for release 15 and beyond. So we want to emphasize that there's a rich technology enhancements even after release 13 and going beyond release 15. So this one we already talked about the positioning locations service provided in the new release. Basically, the UE will measure the timing from different nodes in order to get the timing. This is similar to today's cellular-based positioning techniques. So on the multicast side, we also looked at different multicast. And the challenge here is to make it both simple and cheap, and also to allow efficient software upgrade. So without much of the physical layer new signals, we basically have the signal broadcast or multicast to multiple UEs from a single cell. This way, we don't have to introduce a lot of physical layer changes. So these are so positioning and multicast. Those are the two most important features for release 14 enhancement, and this will have impact on the easy firmware upgrade, longer battery life, and so on, and also provide better capacity from the network point of view. So now we're in the third section where we talk about the ecosystem adoption for the lte-IoT. We also discuss Qualcomm's product offering and how we are leading the IoT evolution to 5G. So mobile technologies drives IoT. We are building our leadership in mobile inventions. As you know, Qualcomm has product offerings in all these listed items. In connectivities, we cover a broad spectrum of all the from Wi-Fi, Bluetooth, 802. Series, and also 4G, 5G, LTE, and near-field communications. We also provide the computing platform. For example, we have techniques like deep learning, auto processing, sensor processing, CPU, GPU, and so on. And also we support all the security protocols. So these are all the important aspects where they are building components for providing the IoT ecosystem, and Qualcomm is providing a broad range of these technologies. one of the key offerings from Qualcomm is MDM9206. So this is a global narrowband solution for the IoT, and it's a single SKU for diverse deployment needs. It is a one hardware design, so supporting multi-mode for Cat M1, NB1, eGPRS, GNSS, and VoLTE. So these are the most important features for IoT, spanning from the low-end nb-iot applications to high-end M1 applications. And also it has positioning and VoLTE support. And it is based on a one software image. So basically we can support different mode selection with flexible configurations. You can configure it just to support nb-iot or just support M1, for example. On our side, we actually support all 15 LTE bands. That covers virtually all of the world. So we have listed the band support here. So this is a very highly cost-effective modem offering, and with faster commercialization. Actually, it is already available as of today. And it's also future-proof with lte-a upgrade. As I mentioned earlier, we have, if there's any software upgrade needed, we can upgrade this as well for the future needs. So what are the design considerations for the trade-off among single mode, multi-mode, and a global multi-mode? So if you look at the category M1 versus category NB1, they have pros and cons in different aspects. For example, category NB1 will offer lower cost, but on the other hand, it is at the expense of lower data rate. Category M1, on the other hand, will offer better mobility, better and the data rate. Cat NB1 will have better coverage, and so on and so forth. So if you just provide a single mode, you can have a very targeted application, but it's not as flexible as having a multi-mode, where we show in the middle. If you have a multi-mode chipset, then you can get the best benefit of pretty much every aspect, except for the fact that, okay, it could be more expensive than just a single mode Cat NB1. The last one actually will show global multi-mode, where we have the global support of all different bands, and also both nb-iot and eMTC. In fact, if you consider the global multi-mode, even cost side, we have the benefit, because now you can just use a single SKU for all the applications, which is significant cost saving, rather comparing to have two different modes, nb-iot and eMTC. So this is one of we further get into the benefits of the global SKU. So we have the saving on the total cost of ownership, because if we have a one SKU to fit all different applications, it will have lower R&D and engineering costs, lower manufacturing overhead, simpler supply chain, and lower inventory management costs. And it will also de-risk end-of-life inventory. So if you don't, in the future, if you don't use certain technology, you can reuse the same single SKU for the other technology. And also time to global launch is faster. Since we have a multi-mode support, this one chipset will fit all the needs from different markets in the world. And of course, there's a higher return on R&D. Once we do this single mode, we can support different applications and so on. So we have a wide adoption of this MDM9206. We have multiple design wins across leading mobile OEMs. We listed a few OEMs here on the right side of the slide. Some recent announcements. We announced the support for Verizon ThinkSpace platform with modules from Quictel and Telit in January of this year. And we jointly demonstrate the performance of successful IoT VoLTE call with Ericsson and AT&T February this year. And we also recently announced the first multi-mode trial with Mobike and China Mobile in May of this year. So we also are pre-certified for major global mobile operators that shortens the time to market. So here is a map of current snapshot of operators' commitments to either nb-iot or Cat NB1 based on the public announcement from these operators. You can see there are preferences for Cat M1 or NB1 in different regions in the world. And some of the operators, for example, in Japan, they actually use both. In Japan, and some of the European operators, they actually use both Cat M1 and NB1. And as you can see, there's a tremendous momentum behind the IoT deployments. And this kind of figures is updated quite frequently to capture different operators' deployments. Yeah, this is a plot to show that we have a broad roadmap across different tiers, ranging from the high-end X20 and gigabit wireless, gigabit LTE chipset, all the way down to category 1, category NB1, and so on. And Qualcomm is providing a broad range of the chipset to support all different market needs. And this is the summary slide. We discussed about IoT. lte-IoT starts to connect the massive LTE today. And also, we continue the IoT evolution to broaden the use cases. And we're driving broadband ecosystem adoption. And we're leading this aspect also for the 5G and the 5G evolution. Thank you. That concludes the presentation part. Then we can open for the questions.
Great. Thank you, Hao. And yes, we are going to move on to the Q&A. I would like to remind everyone that there's still time to submit questions using the Q&A widget at the bottom of the screen. We have lots of great questions already, so we will go ahead and get to it. Let's get started with this one. How will eMTC and nb-iot split the IoT market? Why are some operators prioritizing one over the other?
Yeah, so from the beginning, we have different design requirements for IoT. Some of the use cases are targeting, for example, wearables. Today's smartwatch, most of the smartwatch either talk to the phone through the near-field communications or Wi-Fi. But if you want to have a smartwatch directly talking to the network, then you would have to have certain data rate. And MTC, which provides at least the lower band version of MTC provides the data rate up to 1 megabit per second, are targeted for those high-end applications. But then for nb-iot, for example, it was targeting the extremely low-cost aspect. For example, if Internet of Things, these small devices can be deployed everywhere, for example, refrigerator, meter reading, and so on, where you only need very, very low data rate, then nb-iot would be the choice. The other deployment consideration is nb-iot with release 13 and 14 doesn't have the TDD version of it, and eMTC doesn't support the standalone operation or doesn't fit into the GSM band. So if some operators would like to reform GSM spectrum, then the choice would be nb-iot. And if some operators would like to deploy TDD, then eMTC would be the choice, and so on and so forth. So, but as we mentioned earlier, these two technologies, they also share many common aspects. So, and that that's one of the reasons that we have the multi-mode offering, so that we can use one single SKU to address both market needs and address different varieties of IoT applications.
Okay, great. Thank you. Okay, Hal, and also, could you please elaborate on the trial with Mobike and China Mobile? What's the use case, and why is multi-mode so important here?
Yeah, so I don't know if everybody knows about this Mobike applications. Basically, it's a shared biking service where the user just scan the 2D code on the bike. Then through the wireless communications, it can unlock the bike, and you ride until you reach your destination. Then you can leave your bike there, and then the next person can have this shared biking as well. So this right now is many of the biking services rely on 2G to connect to the network, but we're considering using the nb-iot or eMTC in the future, so that they can directly talk into the LTE network. Will be much more efficient. And also, if any companies want to have worldwide deployment, say Mobike, for example, is in China, but if Mobike wants to go to Europe or wants to go to US, then the global multi-mode chipset will allow them to use this single SKU to have product development. And once the bike is ready, it can be shipped either into China, to Europe, or to US. And there's no need to separately manage different bikes with different SKUs. So in a bigger picture, this will have a lot of savings, and it makes the management and the product development a lot easier. So that's the main benefit of this global multimode chipset we're offering.
Okay, great. Okay, and another question is, so will Release 16 for IoT be compatible with eMTC and nb-iot? With a 10-year plus battery life, is the LTE network expected to remain operating for another 10 years?
Yeah, this is a good question. If we look at how long 2G and 3G network lasted, even today we have some GPRS and 2G network in the market. So I would say that LTE, given the world adoption today and the ubiquitous coverage today, LTE will be in the market for quite some long time. And 5G, for example, is the first deployment will likely come up in the 2019 to 2020 timeframe, and it will take time for 5G to provide a worldwide coverage. So today we're deploying nb-iot and eMTC, which has 10 years of battery life. That will last a while. So LTE can support the nb-iot and eMTC deployments of today, and I don't think that would be a problem that it will be replaced by 5G or any other future IoT devices.
Okay, great. And so what's the difference between voice support in Release 13 and Release 14 with enhanced voice over LTE? Voice is already supported in Release 13 for eMTC after all.
Yeah, so the VoLTE support in Release 13, basically the basic support is already there, but in Release 14 we did some enhancement to shorten the latency and make it a better coverage enhancement for VoLTE. So basically is some enhancement needed to make the voice support even better. So in terms of, mostly in terms of latency and coverage side. But in theory, Release 13 already support VoLTE. Okay,
great. And getting back to 5G for a second. What are the main motivations for 5G MMTC?
Yeah, so when we are looking at 5G MMTC, some of the regional requirement is to have to continue to have all the aspects that 4G LTE or nb-iot eMTC support. In addition, there's an aspect of massive connection. So some of the more advanced techniques will allow this massive connection to happen. For example, the non-orthogonal multiple access, and also some of the techniques can be more efficient in the 5G. For example, the relay and the mesh network. So some of these techniques are more drastic changes than just say increase the bundle length or increase the data rate for nb-iot and eMTC. So at that point, it will be hard to call either it was nb-iot evolution or this is a 5G MMTC. But we are considering all the research directions, including the clean slate 5G MMTC. So 5G is designed today with URLC and eMBB. And there could be IoT, 5G IoT, which is clean slate design, which is takes into account all the 5G specifics and remove all the legacy support from LTE and so on. But that will come later down the road. It's not immediate consideration. At least for current 5G standard side, the focus is on eMBB and nb-iot. So for 5G IoT, centric IoT, or clean slate IoT will happen someday in the later releases.
Okay, great. Okay, and you mentioned in release 14.15 that the bandwidth supported has increased to 5 megahertz from 1.4 megahertz for eMTC and 200 kilohertz for nb-iot. So how does this impact the battery life coverage and throughput?
Yeah, it's a good question. It's always a design trade-off when we want to have higher data rate and so you can either have higher data rate or lower cost or longer battery life. So these all design aspects are pulling in different directions. So what is the best compromise? And for example, in the IoT applications, there could be applications that require a much higher data rate. In that case, you may want to consider even higher category than nb-iot or eMTC. For example, you can use some of the applications can use category 1 and above. So back to the battery life saving, if you are looking at 5 megahertz system and providing higher data rate, it is possible that this application will be more often waking up or will transmit more data and so on. So the battery may not be 10 years battery life. And this type of application, typically, for example, for the high data rate, could be video streaming, could be high quality audio to the wearables. And this type of applications, typically people still looking at charging once a while instead of leaving just on the battery and last for 10 years. So the 10-year battery life applications, typically we're targeting the meter type of applications where you deploy the meter, then you leave it there for many years, and it only transmits sporadically, so once or a few times per day. So these are slightly different applications. I think most likely if you have a video, audio, high-quality streaming for using 5 megahertz, then that kind of applications will be recharged more often than 10 years.
Mm-hmm. Okay. And we have time for one final question, so let's wrap up with this. What percentage of today's IoT deployments use eMTC versus nb-iot?
Oh, that is a hard question. I think the closest guess is look at the picture I showed in the worldwide deployment. Right now, many operators, they either just announced or they are doing trial. For example, in China, all 3 major operators, they are committed to nb-iot and eMTC. They have many trials going on now, but it's very hard to tell how many people are actually subscribed or how many people are in the trial. And similarly, if you look at Vodafone, who is aggressively pushing for IoT in Europe, and also Verizon is deploying and AT&T deploying in the US, they all have many deployment already in these different markets, but it's very hard to tell which one, in terms of percentage of how many users of one versus another. The closest would be look at the operators split in the map I showed, where you can see how many operators are using nb-iot today, how many using eMTC today, and how many are using both.
Okay, great. We're going to have to leave it there. Thank you so much, Al. And just a couple of final housekeeping notes. I'd like to remind everyone that this webinar has been recorded, so you're going to be able to access the recording within 24 hours just using the same page you used to register for the event. And with that, thank you for attending the Fierce Markets webinar and submitting so many great questions. I'd like to thank our speakers for participating and Qualcomm for presenting today's webinar, and we look forward to seeing everybody at future events. Thank you very much.
Thank you.